Thanks very much for the introduction, the invitation, and attending my talk. As a mechanical engineer, when I arrived in Heidelberg and in Germany, has been always my dream speaking about my research at TUM, where there are so many colleagues that contribute significantly into my field in robotics and in automation, and also several friends for whom I have an unconditional esteem. So what I would do today is speaking about my path and the path of my team over this last 4 years in Heidelberg University. And I will mostly talk about how to use machine learning and control system design for mastering the instability and the nonlinearities of soft wearable exosuit. That is the main pillar of my research. The name of my lab is ARIES Lab, stands for Assistive Robotics and Interactive Exosuits. And over the course of the year, as a team, we grow quite a lot, starting from, let's say, 10 people, and 19 of April 2023. This one was my celebration for the birthday. So I passed 46, I turned 46 on the 19th of April, and this is my team, my complete team. We are quite diverse, a lot of visiting students, a lot of people from several countries. I'm very satisfied with them. What about my research stream? I have several research streams. I would say starting from wearable robots and rehabilitation engineering. I do also something in computational biomechanics that I use mostly for design purposes, but mostly mechanical design, I would say, that is, and mechatronics is our main core of specialization. I started with rehabilitation robotics. So they were the people, it's a big delay, sorry, this, I don't know why. I started in 2005, joining the group of Neville Logan and Igor Krebs, and this was me. Then we met again in 2022. They were more or less the same. I was changed a lot. They were always smiling a bit more rather than 2015, more relaxed. In 2005, I would say they were super aggressive. I consider them my mentors for my career. They were the people really that helped me, and they gave me the boost for continuing into research. My first experience was in rehabilitation of hands. At that time, MIT was basically focused on restoring hand motor function. They were the pioneers in rehabilitation robotics, but mostly for upper limb, not the hand. And then we came up with an idea of using a very simple mechanism, let's say a crank and sliding mechanism in a multiple configuration to simulate hand grasping. That was the main action that you want to restore in people that are affected by stroke. This kind of system then became part of a company that at the time was named Interactive Motion Technology, and is a device that is quite widely used in the US for hand rehabilitation. Once I came back to the Italian Institute of Technology, I wanted to design my own systems. This is, you know, my behavior. I want to design my own technology, and it's the same philosophy that we use in our lab. And I designed a system for wrist rehabilitation. It's a system that mobilizes all the 3 degrees of freedom of the wrist. It works as a haptic system with a virtual reality environment. I use it for several purposes, starting from general haptics, visual motor rotation, mastering of a virtual object with intrinsic elasticity that can be simulated by manual manipulation. Then I wanted to test myself on the ground of neurorehabilitation, using this kind of things also in people affected by stroke, mostly adults, but also I have some experience in cerebral palsy, that is a stroke actually that happened in the very early stage of the developmental process in children. We have a collaboration also with the University of Pittsburgh, with Marco Capogrosso, that does implants, neural implants, and we use this technology just to test if these neural implants enhance the capacity of motion of this person. When I just start testing myself also on biomechanics, I wanted systems for measuring musculoskeletal stiffness. At that time, the idea is using big manipulators for measuring human arm stiffness. I wanted to design a system that was able to measure the stiffness in 960 milliseconds, while before it took more or less 20 minutes. What we do also in Heidelberg is studying bimanual manipulation using, let's say, bimanual exoskeleton. We have our own proprietary software for simulation of bimanual coupled interaction. And we use, of course, a commercially available exoskeleton, including also electrical stimulation. I'm not going to talk about all these things. What I want to talk is about wearable technologies and exoskeleton. The first example of exoskeleton dates back in 1967 when Ralph Mosher, that was an engineer of General Electric, wants to design his own exoskeleton for industrial purposes. That was quite a powerful system, but in terms of control, no, it was not at all symbiotic, even if it has been, let's say, defined as a symbiotic unity. Now, the problem is that at the time, control system design was mainly extracted by automation and didn't rely on human-machine interaction. That was, let's say, a theorization and a formalization of regular and classic control into interaction with men and robots. Over the course of the year, this approach shifted from a very rigid exoskeleton, highly powerful, but very low bandwidth of motion, to exoskeletons that are intrinsically softer, with higher bandwidth, however, with a lower force. Now, it's not that one represents the evolution of the others, because rigid exoskeletons are still widely used, especially in people that are affected by spinal cord injury, because they can really sustain the weight of the person. However, I would say that if you want a very powerful system with low bandwidth of motion, you will go for a rigid exoskeleton. And if you want a system with not a huge power-weight ratio, but yet a very high bandwidth, you will go to exosuits, and you will use exosuits. Now, what is an exosuit? An exosuit is a wearable system that does not involve transmission of motion via rigid links and rigid hinges, but it's composed by textile, and this textile includes both the actuation and the sensing. You rely on your biomechanics to transmit motion using physiological joints and actuating a different kind of system. In this example, you see a tendon-driven system in such a way to mobilize, in this case, the elbow. There are several exosuits. Let's say that the first example were in lower limb, with different kind of actuation, tendon-driven, pneumatic actuations, hydraulic actuation. Who were the pioneers? The Biodesign Lab of Connor Walsh in Harvard. They were the ones starting for first. How an exosuit works? Well, in this kind of application, you have to detect the walking phase, and then coordinating the electromechanical actuation that will do tendons in order to propel your walking phase. Okay, in this case, you are propelling the ankle joint. You extract everything by motion. You can close the loop using the force control. You can use a variety of controller. There are also examples in upper limb, more or less using the same technology. However, upper limb or lower limb, they are quite different. Not only for what concern, let's say, the amount of force and assistance that you have to provide, but the typology of control that you will use to detect or classify the motion of the legs or the motion of the arm. That is characterized by a much higher dexterity with respect to the legs. If you want to design an exosuit, you have to deal with several, let's say, pillars of research, starting from how to distribute sensing, understanding about control, designing the physical interface, choosing the actuation principle, study also the ergonomics of the systems. If we want to summarize this kind of concept, we will go with three main pillars: ergonomics, actuation, and control. I'm not an expert in ergonomics, and there are people here in TUM that are by far much better than me because they are actually ruling the ergonomic field in Germany, and they are quite known also for what concerns classification and testing exoskeleton and exosuit. But during the talk, I will talk mostly about our experience in control and actuation. Now, what can I say about actuation? We are usually inspired, let's say, by the musculoskeletal system that remains unmatched in terms of power-weight ratio and bandwidth. But what I do is mostly using electromechanical actuators, and these electromechanical actuators have electric motors and pulley that pulls cables that are I would say, a tendon-driven actuation. Then we can use several other actuators, pneumatic muscle or median, twisted spring actuators, shape memory alloys, or pneumatic inference actuators. I am very much into electromechanical actuators also because you can use all the theory and the control system design that derives from classic automation. Now, how can you drive an exosuit? This is a glove exosuit. You see here the actuation. Inside this glove, there are small sensors that detect the amount of motion of your fingers. And then you basically send this information of motion, so you have to detect the motion of the person, to the actuation. The cable, of course, are routed around the finger. There's always a problem related to how can you route the cable around the finger not to transmit parasitic torques. What we do is we use also 3D printing, additive manufacturing, and we have a parametric program just to measure some parts of the hands, sending everything inside a program that starts a 3D printing system. We need, few hours. We go to the hospital, we measure the hand of the patient, we come back, we start sewing a bit, printing every single components, and then after you have printed the single components, you can basically assemble in one day this device attached to the actuation and having something that is completely tailored to the anthropometric of the person. Okay, you have a better distribution of force, a better transmission of force, better fitting overall of the system. From this kind of approach, one of my students, Ryan, created a startup that is called Power Orthotics. I think that I skipped. This guy is based essentially on the same technology. We have a system that is completely 3D printed with an actuation that is extremely compact and embedded. And it works in a very simple but working principle. That is, for example, a pressure-sensitive band on the unimpaired hand. You can actually command the system via voice control, open or close, or you have also an app on the phone. We test the system quite extensively, I would say, with the Spinal Cord Injury Center that is in Heidelberg University. We have a collaboration with them. Here you see the subject that is affected by spinal cord injury. It's not completely spinalized, but doesn't succeed in firing the muscles enough to close the hand. With this kind of device, you can provide additional force and torque in the grasping phase and allowing the person to grasp simple object or let's say start a compensatory strategy for activities of daily living. Now, let's go into a more technical description of how we control this kind of things. If you want to control upper limb or lower limb, these are two separate domains, completely different. And there are also two separate domains, not only for what concern what kind of signal you have to acquire, but also what kind of force you have to deliver. If we start with upper limb, you need to understand what is the signal. Here is indicated as force reference that you want to send inside the low-level control, that is the one that actuates the electromechanical actuators. For upper limb, usually this kind of approach is an admittance control. You detect the force at the interaction with the exosuit, you send inside your controller, and you generate a velocity in order to command the actuators. Now, for control of upper limb, the first approach that you can have is using what is called a dynamic model or dynamic arm model, or is a force gravity controller. How does it work? I have inertial measurement units, so I'm not detecting any biosignal, but only motion signal. And the configuration, the three-dimensional configuration of the arm is communicated to the controller instantaneously. The controller has embedded a mechanical model or a biomechanical model that is tailored on the anthropometric of the person that is wearing the exosuit. And then you compensate for gravity in a very simple way. The force sensors detect the force on the back. Two inertial measurement units communicate to the controller that is posed on the back of the person where the actuation is, the three-dimensional configuration, and as soon as you move, the system compensates for gravity and provides you assistance. Now, what's the problem with this kind of controller? Well, if we take two different motions, three different motion at three different velocity, the problem that you will have is that when you accelerate, when you have a higher velocity moving your arm, you always have a delay between the desired trajectory that you want to execute and the assistance of the exosuit. This delay increases the faster you move. And of course, what happens is that the accuracy of motion is jeopardized. This means that since you are not detecting the motion before it happens, but you are measuring the force at the interaction, the system will have a delay that is, of course, dependent on the amount of velocity. It has a reduced bandwidth. This happens not only kinematically, but it happens also dynamically. This green line is the amount of biological torque that you have to input when you are moving faster. So it means basically that the faster you move, the lower the exosuit will be able to deliver the force, and the higher is the amount of force or torque that you have to generate. This is a problem with system that works in pure force control. Now, the question is, how do you solve this kind of problems? You have to detect the motion before it initiates, but to do that, you need to extract some kind of biosignal. The first biosignal that you have in mind, of course, is electromyography. You know that there's a delay between our ion channels that open and generation of motion that is called physiological electromechanical delay. It's a sort of bandwidth, intrinsic delay in our muscles, is between 60 milliseconds and 150 milliseconds, depending if you are moving large muscle or small muscles. So the idea is, can we include electromyography in the loop, and how can this electromyography be used in order to drive an exosuit? The idea came when I was with my friend Massimo Sartori, a colleague also, at the University of Twente. He's a person extremely skilled in computational biomechanics, and we use what is called a myoprocessing technique. A myoprocessing technique is not an EMG control. It's usually a proportional control. You extract the EMG and you send a signal. No, a myoprocessing control utilizes different blocks that relies on two signals: inertial measurement units that provides you the motion of the arm, and electromyography. These three different blocks are this kind of block here. An activation dynamic, that is a function that tells you respect to the EMG that is input, how much your muscle is contracting. The joint angle that are given to you by the inertial measurement unit that tells you what is the velocity, so the kinematic of the muscle, for example, the biceps. And these two signals goes inside the muscle tendon unit dynamics that extract the force, for example, of my biceps. Now, what do you do with this force? Well, you have to send this force inside a computational model of your upper limb that is exactly tailored on your anthropometrics. In this way, you succeed in generating a torque that is sent to the motor, and the motor compensates with a certain kind of accuracy for your weight. The myoprocessing technique uses this different approach rather than a proportional myoelectric control. Now, how fast you can go? Well, you can go pretty fast. You hear the actuation. Corona time. We were allowed to stay at the university, but I mean, now, which is the best between the two, you will ask? Well, after what I've said, probably you will say the myoelectric control. No, let's say that's not a clear winner. It depends how you design the overall mechanics, how you choose the controller. So let's make this experiment. Let's implement inside the embedded controller both the myoelectric and the force control. And then let's test people without telling them which between these two controllers are using. And you can do it in in three different ways. Just testing the accuracy of the controller in fine motions, testing the bandwidth, how fast you can go, and testing the stability that is paramount in this kind of application. If we test the stability, for example, we have something like this. Microprocessor, dynamic arm. So the person is blindfolded, and there's a big 1.2 kilo that is falling down. And then you study two main parameters. This is simple control engineering. Rise time, so response time of the controllers and the actuators, and settling time, which between the two controllers stabilize at first. Well, I can tell you that between the two, for sure, the one with electromyography detects at first the impact of the ball and reacts at first. So react faster with respect to the force control. We are talking about more or less 300 milliseconds versus 400 milliseconds. These were tested on 12 subjects. But in terms of stabilization, the force control stabilizes at first. It's more stable, as a settling time that is short. Now, the reason is, I don't know, I'm speculating, noise in the electromechanical signal. However, what I can summarize from this slide is that none of the two is winning, 1-to-1. If we consider anyway the capacity of actuation between the two controllers, so as soon as I attempt to move, which is the one that reacts much faster? Well, of course, is the microprocessing system. The microprocessing control succeeds with this kind of architecture in giving you an assistance, a mechanical assistance, as soon as you attempt to move, that is in the order of 60 milliseconds, that is comparable with the physiological electromechanical delay for the biceps. If you have the pure force control, when you attempt to move, the system will detect the motion and generate an amount of force in 150 milliseconds. Now, of course, there's a significant difference, but 150 milliseconds is fast enough. You have to move very fast to feel that there's a delay between the exosuit and your motion, even if you are controlling it only in force. However, I would say that if you start playing with this controller, you can go pretty fast, and at first sight, if you look hand on other systems that you have to look in exosuit, never fly with both the controllers. Where the microprocessing technique win without hesitation. If you move different weight, starting from 200 grams, 500 grams, and 1,000 grams, if you look at the amount of torque that is generated by the electromechanical actuators in pure force control, you see that it doesn't change depending on the external weight that I am lifting. So it does not adapt to the external load. You should actually enter the program and increasing usually the proportional controller in the PID that is at the low level. But with the microprocessing control, without changing any gain, if I grab a heavier object, the assistance of the system will be higher. There's this automatic adaptation that depends on the initial part of the electromyographic signal that is detected. Of course, you can arrive to a level of assistance until you do not saturate the electromechanical actuator. How you can, if you don't want to use electromyography, because this is always a problem, electromyography is a signal that changes over the course of time depending on the skin impedance. If, for example, moves, you wear the electromyography under the exosuit. And if you don't want to use electromyography, the only way of detecting an object and then shaping the actuation is using vision. We remove EMG, we use only the force control, but we have a camera that detects the weight of the object. This is quite a preliminary work, but we are progressing. And depending on the weight of the object, once the object is recognized, when I grab the object, the system automatically increases the assistance. So in this way. So the person has a camera that is here on the chest, and then as soon as you look at an object and you stabilize, this object is recognized. When you grasp it, the system understands that you're grasping the object and recalculate the gravity of your arm plus the one of the object. Of course, you need to train the system with a database of different objects. If it's an object that is not trained in the database, it doesn't know what kind of assistance provided to you. What are the clinical applications for this kind of technology? Well, we tested our system operating solo line force control with people affected by spinal. This one was an experiment that has been performed in Italy on a C5 that was highly impaired, but still with a, let's say, residual capacity of motion. The person, when the exosuit is not active, does not succeed in moving. But as soon as you activate it, and of course you have to trim the sensitivity of the controller in a certain way, he's able to amplify his motion, obtaining or using those residual capacity of motion to move the arm. And then, I mean, of course, this is not a, let's say, a functional motion. However, he can exercise. On this kind of approach, we wanted to test this kind of technology on multiple sclerosis patients. We have a collaboration with the Italian, I'm Italian, of course, I mean, for probably you understood, with the Italian Association of Multiple Sclerosis. And we want to provide this technology for enhancing endurance. The problem of multiple sclerosis is then when they start the rehabilitation program, they don't have enough, let's say, endurance. They stop exercising. If you provide this kind of technology, they're able to exercise for a bit more time. Now, what we do is we provided this exosuit, and we ask this person of lifting object in a repetitive motion. And then what we get is that using the exosuit, respect to without using the exosuit, they reach a better range of motion, smoother movements, yet no change in the physiological motion that they had before. If you look, for example, what happened with high-density MG, that usually is here on the biceps and on the triceps, what you will have is that there's a lower activity with the exosuit, and they endure much more in terms of time in holding an object before they encounter muscular fatigue, before you start trembling. So all this kind of approach is an approach, basically, that tells you that using this kind of technology may allow people that are affected by neurological disease of having a higher endurance during rehabilitation programs. Another things that we also do with softwareable exosuit is merging functional electric stimulation with this kind of approach. What is functional electric stimulation? Functional electric stimulation is a common therapeutic approach in which current is injected in your muscles to provide contraction and avoid muscular atrophy. This is something that works pretty well, but there's only one problem. Well, two problems, I would say. The first is that injecting current in the muscles is not something very pleasant. And the second is this way of injecting current provide recruitment of large muscle fibers. And the motion that is provided by the person is very abrupt. Plus, since you are recruiting large muscle fibers, you have much consumption of oxygen, and you encounter onset of muscular fatigue much earlier. So you have to switch the system off. The idea was considering integrating inside the controller of an exosuit commercially available functional electric stimulator provided by Charles Timmerman, that is Metal, that is a company from Hamburg. And the system is able to communicate via Bluetooth Low Energy integrated inside our controller. So we are able to detect the motion, and at the moment we detect the motion, we split the assistance between functional electric stimulation and assistance from the exosuit. You can use the functional electric stimulators or the stimulators itself to measure residual EMG. So the person attempts to move, but has an EMG that is very small. Of course, this is not a subject, it's a completely super unimpaired person, is a student. When we measure the EMG, this amount of residual EMG is sent inside the controller splits between the current that is decreased on the functional electric stimulators and the amount of torque that allow to lift the arm. In this way, we are still able to assist people, but we are also able to inject current in the muscle, avoiding muscular atrophy. The results is more or less similar to the one with functional electric stimulator. Once we, oops, me try again. This is with functional electric stimulator, and it contracts very abruptly. And this is with functional electric stimulator plus exosuit. What we obtain is that if we ask person to make repetition before encountering muscular fatigue, the person that are using the hybrid controller, the one with functional electric stimulator and electrical and electromechanical assistance, are able to exercise many more time respect to people that are not using the exosuit. We do also human augmentation in industry. We have a collaboration with Comau and Munich. This is a German company. I will now present what we do with Comau. What we have done is integrating a commercially available exoskeleton that is a passive exoskeleton for overhead walking with a layer that is soft and actuated. In this way, you have a hybrid system that is a system with active and passive, rigid and soft architecture. So you see, this is the elbow exosuit. Now, you can use this kind of things, of course, for lifting. And then you have to test if the system is effective. How do you test it? Well, someone from the mechanical engineering department will tell me to use the exoskeleton assessment test that actually was designed here by Professor Bengler, but we didn't have the metabolic analyzer at the time. So you need a metabolic consumption analyzer. So something that you can say is there are papers that demonstrated that using this kind of exoskeleton increase the co-contraction of the muscles. So this means that when you use this kind of system, you correct your trajectory several times. Is an expenditure of energy, is a disruption of the physiological motion. I think it depends also on the adaptation to the system. I mean, after a while, probably you master, the assistance of the system and you know how much you have to fire muscles. However, we measured the co-contraction index using this kind of approach with and without the exosuit. And then we noticed basically that after a while, there's no co-contraction between different muscle agonist and antagonist after you exercise and you train yourself. Now, let's start understanding now. Let's cancel upper limb. Let's go to lower limb because lower limb is completely different. In lower limb, you use always a sort of force control, even if in our approach, we don't use force sensors. But the important is how do you understand what is happening at the walking leg? You have to understand and detect the phase gate. Who were the pioneers? Of course, Biodesign Lab, Connor Walsh. They published several papers and they demonstrated that on treadmills, so in lab, they have 15.4% or 7.4% respectively walking and running of reduction of metabolic consumption, oxygen consumption. Okay, it's the cost of transport usually. There's a group of Robert Riener from ETH that use a proprietary technology from a spin-off that is called Biodesign. This is exoskeleton here. And outside, so it means outdoor, they have roughly, let's say, 10% of reduction in metabolic consumption. The group of Steve Collins from Stanford has a rigid exoskeleton using machine learning to optimize the assistance depending or tailoring the system on the gait of the person that is wearing the exosuit, 17%. Cost of transport outdoor. They were walking around this building. Now, we do have our own technology that consists in several architectures. The first architecture that we designed was an under-actuated system with a single motor here that pull and release the legs, depending what kind of leg is, let's say, stepping forward. Is a hip exosuit that assists in flexion. The system works with Bluetooth low energy, inertial measurement units that communicate everything or the gait phase detection to the controller that is here on the belt. And then, as you can see, we don't use any force sensors, yet the cable are always in tension, they never slack, without using force sensors. We have also another system that is much more powerful. The system consists in two motors, so one motor for each leg. And then how do we control this kind of system? We have our own controllers that works using heat phase reconstruction, so velocity and position extracted by the initial measurement units, and some kind of Kalman filtering to polish what happens from the signal of the initial measurement units. The system is extremely stable. The cables are always in tension. You can walk over the stairs, you can go down the stairs, and now I will show you some examples. But then, of course, we want to test this controller independently on the hardware architecture. Two motors and an under-actuated system. Does it work? The same controller? We tested outdoor, where you can test in Heidelberg on the Philosophenweg. That is a very nice walking pattern in front of Heidelberg castles. We tested the system for a walk of 1.2 kilometers on unimpaired people, of course. And it's quite a big walk because the distance is 1.2 kilometers, but you have 216 stairs and 40 meters of ascension or descending, depending if you go up or down. And what we obtain with this kind of things, let me see if you hear the actuation. We have 20% reduction in consumption of transport for the deactivated system, 11% in the single system with one motor. This is what we obtain. Okay, so here you see the actuation rotating here. The motors is that you hear is the oxygen cell. Now, we tested also on elderly population. And I have to say that the German grandparents actually walk quite fast. 73 years old, and my students that is struggling to stay with her and collecting the data. So here we did it not on 1.2 kilometers, but we did it with the Institute of Sport Science that is in Heidelberg on a 400 path in the track and field. What we obtain, well, also here, there's a significant decrease. This guy, 14%, 12%, it changed, yet it's significant. Now, how we can use artificial intelligence with this kind of approach or machine learning? I mean, why it can be useful in this kind of science? Well, let's say that the main idea of using an exosuit is synchronizing the walking pattern. But if you do it in the lab on a treadmill, it's quite easy. Or I mean, unless the treadmill doesn't explode at one point, nothing happens. If you walk outside, there are some change, U-turns, speed change, ramp. So you need to predict and put the system in phase. Predict or classify what is happening. In order to have to account for sudden change in the walking pattern. How you can do it? Well, we use machine learning. We have a normal adaptive oscillators layer that is more or less similar to the one that we use for driving the exosuit, but then we have a machine learning layer that is trained with data that are detected while walking. You create a data set. You put everything in this data set, you give it to the machine learning layer, and then at the end, you test your exosuit. What you obtain is a system, the cable never slack, that in different conditions preserves a continuous assistance without never slack. Well, of course, you run and start slack. But it decently works. Now, the question is, how do you test if it works or not? Well, I can tell you that here for the cable that does not slack works, but then you will ask me, well, I would like to have something numerically speaking. Yeah, you're right. So you can test metabolic consumption on the treadmill at velocity 0.6, 0.8, 1.1 without the exosuit with the exosuit without the machine learning layer and with the exosuit with the machine learning layer. You see that with and without the machine learning layer, there's no significant differences between the use of exosuit on the treadmill. But as soon as you step outside, the difference between using the machine learning layer or not is significant. And it goes down over 10% in the trial that we have done outdoor. So it's not that the system is not working without the machine learning layer, but you can trim it better. You can provide that boost in terms of capacity of the system of providing the assistance, even if in condition that normal controller do not detect, is an additional layer. You can use this kind of things also for other applications. For example, sit to stand. So, same models, here the cable are for the extension. Then we have detection. As soon as you go down, the system assists you in sitting. When you go up, big click, because it detects that you are standing. Again. My computer. Well, you understand how it works. Now, and what about stairs and level ground? There's another application. Well, stairs and level ground can be detected using a machine learning approach, this time not using 2 inertial measurement units, but using the third one. You train the system, you take 3, not me, the students, take 3 inertial measurement units and climb stairs and stairs and stairs. And then you extract the data, you feed it to the program, and then you start walking. Level ground, detection of level ground is a motion. As soon as I climb the stairs, ascending stairs, and look at the motion of the system. It's assisting you more. So, ascending stairs. Now, you look what happened when I go on level ground. There's misclassification, but then reclassification from descending to level ground. Now you will say, okay, it misclassified, it's quite dangerous. These are soft exosuits, you can backdrive them. So it's not a rigid link that's moving your legs. It will not assist enough, but then you can backdrive. You go down from level ground, descending stairs. Does it work? Well, let's test it. First of all, you have almost plus 90% of classification accuracy. But then, if you take the metabolic consumption, as soon as you inject the machine learning layer for detection of stairs, it goes down also here. And we tested on the 7th floor, back and forth. And what about using artificial vision for detecting stairs? You can do it. You can spend $100 for a Logitech camera. I'm not working for Logitech, whatever camera you want. And then you have the camera here on the belt that detects with anticipation where the stairs are. You have, of course, to train the algorithm with images of stairs, but there are a lot of databases. There's one provided by the University of Waterloo. It's called ExoNet. You can use that one, or you can just go around with the camera on the waist and detect and collect a lot of images. You have a classification accuracy that is slightly lower, however, quite good. We go more or less over 90%. And then here you are working level ground. Here the actuation. You are going down. Now you go up. The actuation pushes much more because it allows you to lift the legs in a better way. Also, in this case, reduction of metabolic consumption that is significant. Can you walk with this kind of exosuit? Not much. You need to have a specific system with a high bandwidth, high force. The one that we have is able to reach 300 newtons. So, no, sorry, 20 kilograms, so 200 newtons. pull a cable of 200 meters. It's actually here, the system. It works with an actuation unit that you can wear, and has a street driving system with a very small motor that rotates at very high speed and succeeds in inverting the motion at a very high speed. The results is the following. 6 kilometers per hour. It's very noisy. Then the treadmill, that it's not a fantastic treadmill. I have to invest in treadmill. It doesn't push. That's it. All right, so I think this one was the last slide. We still don't have results for this because actually we activated the system a week ago, but we have the system that now we will show because my students brought this device. So the nasty question to them, not to me. I would like to thank my team that actually, you know, is fantastic. I have to say, I have dedicated a lot of time to them, but I think that in this field, we are probably quite solid. All my collaborators, I would like to advertise as, where is Christina? Somewhere there. Said that 1 for September 2024, we will host IEEE BioRob. I will be the general chair. And I hope to see you numerous, especially from a strong university like this one. And then this was my last slide. This is the video that we shot on the Philosophenberg using a drone, actually. And we have also a small drone for shooting this kind of video. Thank you very much for the attention. Thanks a lot.